In this tutorial, we're going to take a look at solution stoichiometry type calculations. And in solution stoichiometry, we always start with a volume and a molarity to calculate moles. Remember, if you multiply the volume times the molarity, you end up in units of moles. And so this is different from our mass type stoichiometry calculations where you start with a mass of a reactant and divide by its molar mass to get moles. In this case, if you see a volume and a molarity, multiply those together, and that's how you get moles. In the first example, it says what volume of 0.1 molar sodium hydroxide is required to completely neutralize 150 milliliters of 0.25 molar sulfuric acid. So you should recognize this as a neutralization reaction. It's an acid-base neutralization. And what we've got are a volume and a molarity of sulfuric acid, and we only have one molarity for sodium hydroxide. So all we have is its concentration. And at first glance, this might look like a dilution problem, but don't go down that road, right? If it's a dilution problem, it only has one substance. Here we've got two different things reacting. So the first thing we should do is write the balanced equation. We've got sulfuric acid reacting with sodium hydroxide. And you should notice that sulfuric acid is a diprotic acid, right? It's got two protons, 2H plus. So this is going to require two equivalents of sodium hydroxide to neutralize that. And this is going to make two water molecules plus the salt sodium sulfate. Okay, so now that we have a balanced equation, we can start this calculation. And you always start with whichever one has a volume and a molarity. So the sulfuric acid has a volume and a molarity. We've got 150 milliliters. Remember, you want to convert that to liters. So let's multiply by this conversion factor, divide by 1,000 milliliters. And now we're in units of liters, so we can multiply by the concentration. And anytime you see that capital M for molarity for the concentration, write it as moles over liters. So we've got 0.25 moles of sulfuric acid per liter. And then we can do our key step, which is the mole to mole ratio. 1 mole of sulfuric acid reacts with 2 moles of NaOH. Okay, that comes from the balanced equation. And then here is where we use the concentration of sodium hydroxide. Right, we're going to divide by 0.1 moles of sodium hydroxide per liter. Right, so anytime you see that capital M, right, break it down into its constituent units, moles over liters, and line those up. And we'll want to convert back into milliliters. So 1,000 milliliters is 1 liter. And notice that you've got 1,000 milliliters over here on the left. It's in the denominator. You've got 1,000 milliliters over here on the right. It's in the numerator. So those actually cancel out. But I'm including all the units for completeness. So we do this calculation, and it's going to require 750 milliliters of 0.1 molar sodium hydroxide to neutralize that amount of sulfuric acid. Okay, so that's a typical acid-base neutralization type calculation. You might also see something like that referred to as titration. Let's take a look at another problem. In this one, we're going to go from a volume and a molarity, right? We've got already, we can see a volume and a molarity to a mass, right? This one asks for what mass of nickel 2 phosphate can be produced from 250 milliliters of 0.25 molar nickel 2 chloride and excess potassium phosphate. So the excess means that we've got potassium phosphate in extra amount. We don't need to worry about running out of that. So the nickel 2 chloride is the limiting reagent. So let's write the balanced equation first. We've got nickel 2 chloride, that's aqueous, plus potassium phosphate, also aqueous, and that is going to form our precipitate, nickel 2 phosphate. And we're going to end up with the salt potassium chloride. Okay, so let's make sure this is balanced. I see 3 nickels on the right, so I'm going to put a 3 in front of nickel chloride on the left. And I see 2 phosphates on the right, so I'm going to put a 2 in front of potassium phosphate. And then you can count up your potassium ions and chloride ions, and you'll find that there are 6 of each of those. So what we want to know is how much nickel phosphate we can produce, and that is a solid precipitate, right? This is a precipitation reaction or double displacement reaction. So that's got to be in grams. And we've got excess potassium phosphate, and we're starting with 250 milliliters of 0.25 molar nickel chloride. So that's what we start with. We've got a volume and a molarity, so let's multiply those together. And at this point, we normally just convert to liters in our heads, right? So we can move the decimal place over 3 to the left and just call this 0.25 liters. And so then we can go ahead and multiply by the concentration of the nickel chloride. So we got 0.25 moles of nickel 2 chloride per liter, right? Remember to translate that capital M into moles per liter. And then we can do our mole to mole ratio, right? We've got 3 moles of nickel 2 chloride, and that's going to produce 1 mole of nickel 2 phosphate. Okay, so now we're in moles of nickel 2 phosphate. We can multiply by its molar mass, right? 1 mole of this nickel phosphate has a mass of 366.02 grams. And so that'll give us grams of nickel 2 phosphate produced. So we do this calculation and you get 7.63 grams of nickel 2 phosphate produced in this reaction.